with this time, we will consider the last application of a definite integral, which is work done by a force. Okay, please take note that we define work as the product of the force and the displacement. Now, when an object moves a distance delta x along a straight line as a result of a constant force F, then the work done by the force F is W is equal to the force times the displacement delta x. But there are times that the force is variable, not constant. So if an object moves along a straight line from x is equal to a to x is equal to b under the influence of a variable force, okay, we shall call it as f of x, then the work done is the integral of the variable force f of x, okay, and we have to evaluate this, the integral in x, okay, limits going from a to b. Okay, now, one of the simplest notion of work deals with the extension or compression of a spring or any material that can be stretched, okay. It can be a spring or it can be rubber, okay, and in here, Hooke's law is applied. And according to Hooke's law, the force it takes to stretch or compress a spring x units from the natural length is directly proportional to x, where x is the elongation. Okay, so if it is proportional to x, then we can use the constant of proportionality. No? If f of x is proportional to x now, if we will replace the symbol of proportionality by an equal sign, then we have to introduce k, and k is the constant of proportionality. So the variable force f of x is equal to kx. Now, in the figure, no, we have here a spring, no, with the natural length L. Okay, up to here, this is the natural length of the spring. Now, when a force is applied, then the spring is stretched from the natural length, no, up to this position, and we call this as the elongation x. So the variable force f of x is proportional to the elongation x, or the variable force f of x is equal to kx, where k is the constant of proportionality. So if we are going to consider, say, a spring, okay, let us have this example. Consider a spring whose natural length is 8 inches and a force of 20 pounds stretches the spring to 8 inches. Okay, find the work done in stretching the spring from the natural length to 12 inches. So if we will consider the spring, okay, this is the spring whose natural length is equal to 8 inches. Okay, so this is 8 inches. Now, a force F is applied on the spring. So if a force F is applied in the spring, then of course it will elongate. Okay, we have a force F. And considering a force F equals 20 pounds, it stretches the spring from the natural length to 10 inches. Okay, so that would mean that this elongation x is 2 inches. Okay, so x is equal to 10. Okay, take note that this is 10 after applying the force 20 pounds. Okay, and 10 minus 8, which is the natural length, will give us the elongation 2 inches. So x is equal to 10 okay, which is the length of the spring after applying the force equal to 20 pounds minus the natural length 8, which will give us 2 inches. Now, according to Hooke's law, the force applied is proportional to the elongation, or the force applied is equal to K times X, where K is the constant of proportionality. Okay, so to get the variable force, we can solve first for K. So force is 20 pounds is equal to K times the elongation, which is equal to 2 inches. Okay, therefore, solving for K is equal to 10. Therefore, the variable force f of x is equal to 10x. K is equal to 10 times x. Okay, hence, since the variable force f of x is equal to uh, 10x, then to get the work done, okay, then the work is equal to uh, the variable force f of x times the differential of x, and the limit will go from 0 to 4. Okay, now to determine the limits of integration, okay, now uh, consider the natural length as 0. Okay, so the best thing to do is, okay, okay, this is the natural length 8, and this will be equivalent to 0. Okay, if the spring is pulled up to 10, okay, so of course this is 8, then 9 and 10, okay, this is 10. So from 0 we will have 2. Okay, so from 0 to 2 means the elongation is 2 inches. Okay, but we are asked to find um, the work done, okay, when stretching a spring from the natural length to 12 inches. So to 12 inches, this is 10, 11, 12. Okay, equivalently, then this will be 4. Okay, therefore, the limits of integration will go from the natural length is 8, so it will go from 0 to 4. Okay, so not from 8 to 12. Okay, if you will have it as the integral from the lower limit 8 to the upper limit 12, okay, that is not the correct way of finding the limits of integration. So equivalently, 8 here will be at 0. So from 8 to 12 means 4 units. Therefore, limits of integration will go from 0 to 4. Okay, so evaluating the integral, of course, the integral of 10x dx is 10x squared over 2, or equal to 5x squared, to be evaluated from 0 to 4. So evaluating x squared at 4 will give us 4 raised to the second power, okay, and multiplying it by 5 will give us 80 inch-pound. So the work done to stretch a spring from the natural length to the length 12 inches will give us 80 inch-pound. Okay, now what if the question is find the work done in stretching a spring, okay, from 10 to 12 inches. Okay, so if it is from 10 to 12 inches, then the limits of integration will go from equivalently 10 is 2 units here. Therefore, the limits of integration will be from 2 to 4. Okay, is that clear? Now, if we are asked to find the work done in stretching the spring from the natural length to 16 inches. So if this is 12, okay, up to 16 inches will give us a 4 more, no? So this is 12, 10, 12, 14, 16. So equivalently, we will have plus 4. This will give us 8. So from 0 to 8, limits of integration will be from 0 to 8. Okay, so you have to consider the equivalent dimensions here, no, to get the limits of integration. Take note that the natural length will be equivalently 0. Okay, so just take the limits of integration in here. Now, another um, application on work is if we want to find the work done in pumping in and out water or liquid in the container, okay, to the top or of the container or to any point above the top. And the work then is W, which is the weight per unit volume of the liquid or the density of the liquid, okay, times H, which is the distance of the element from the point P, where P is the point where the water will be pumped to that point P, okay, and dV, the differential of V is the volume of the element. So that if we have a container here and this is the element, of course the element is in the form of a disk. Therefore, to get the differential volume, okay, since this is circular, okay, and this is the radius, the thickness is delta, let us say that the differential of H is the thickness. So the volume is equal to pi r squared times the thickness. Okay, so this is the differential volume. And H is the distance of the element to point P. We call this as H. So the work then is equal to the density times the integral of H times the differential of the volume. So to illustrate, let us consider a conical vessel. No? We have a conical vessel uh, full of water, and the vessel is 16 feet across the top and 12 feet deep. Find the work required to pump all the water to a point 2 feet above the top of the vessel. Okay, so let us consider this as the y-axis and this as the x-axis, and consider this as the conical vessel. This is in the form of a right circular cone. Okay, now, of course, the y-axis, okay, is the vertical line here, and the center of the conical tank is on the y-axis. Okay, now the conical vessel is 16 feet across. Therefore, from the y-axis up to this point is 8 feet. This is also equal to 8 feet. And the vessel is 12 feet deep. Okay, we are asked to find the work required to pump all the water in this conical vessel to a point which is 2 feet above the top. If this is the top of the vessel, okay, then we have point P here, okay, which is 2 feet above the uh, top of the vessel. Okay, so if we will consider the element, okay, we can draw the element here, okay, with the radius r, and the thickness is, of course, dy. So the element will be in the form of a disc. Okay, this is the element. Okay, the height is, or the thickness is the differential of y, and the radius of the element is x. We shall call the radius of the element as x, since this point will have the coordinates xy. Therefore, this distance is equal to x, and the distance from the x-axis is y. Therefore, if we will consider h, which is the distance of the element, no, from point P, okay, this is h, then that will be equal to, okay, take note that the vessel is 12 feet deep, and from the top of the vessel to point P is 2 feet. Therefore, from the x-axis to point P is 14 feet. Hence, h is equal to 14 minus y. Okay, from point P to the x-axis is 14. Okay, from the x-axis to the element is y. Therefore, h is equal to 14 minus y. So h is 14 minus y. Now, what about the differential volume? dv is equal to, take note that the radius is equal to x. So since the volume is equal to pi r squared times the thickness, okay, or the height, then the differential volume is equal to pi r squared times the height. Or since the radius is equal to x, then we have pi x squared times the differential of y. So using a formula, the work done is equal to the density of the liquid times the integral of h times the differential of v, limits going from a to b. Okay, please take note that since the vessel is 12 feet deep and all the water in the vessel will be pumped to the point P, then the limits of integration will go from y is equal to 0 to 12. Okay, so 0 to 12. And h is equal to 14 minus y. The differential of v is pi x squared dy. Okay, now since the variable of integration is y, we have to express the radius x in terms of y, and we can do that by ratio and proportion by considering the triangle form, no, on this conical vessel, okay, on the xy plane. So if we will consider the triangle form, the right triangle form, okay, the height is 12 feet. This is equal to 8. And if this is the element has radius x, and this is y. So we were able to form two right triangles. Okay, this small right triangle and the big right triangle. So what is done here is ratio and proportion, okay, base to base. Okay, so x is to 8. This is proportional to the altitude of the small triangle to the altitude of the big triangle, which is y. So we will have x over 8 is equal to y over 12. And if we will solve for x is equal to 8 over 12y, or x is 2/3 y. Now, you can also do it this way, no? Okay, you can have the base of the small triangle to the height of the small triangle, and this is proportional to the base of the big triangle, which is 8, is to the altitude of the big triangle, which is 12. So we will have x over y is equal to 2 thirds. And if we will solve for x, x is equal to 2 thirds y. So of course, basically it will give us the same value of x. Okay, so we can replace x here by 2y over 3, then square it. Of course, the square of 2 thirds is 4 over 9, and we can write it before the integral sign so that we will have 4 over 9 pi times w, okay, integral of, okay, then multiply 14 minus y by y squared. So that will give us 14y squared minus y cubed, okay, and we will evaluate the integral in y. The integral of 14y squared dy is 14y raised to the third power over 3. Integral of y cubed dy is y to the fourth over 4. Then evaluate the integral from the lower limit 0 to the upper limit 12. Of course, if we will evaluate the integral at the upper limit 12, then simply replace y by 12. And the value of the integral at the lower limit 0 is equal to 0. And the result when y is equal to 12 minus when y is equal to 0, multiply it by 4 over 9 pi times w will give us the work done is equal to 1,280 pi times w foot-pound. Okay, so please do not forget that if we have problems like this on, say, conical vessel, no, we can always do ratio and proportion since we can form two right triangles. And last example, let's have the third example. Now, this time we have a cylindrical tank. And a cylindrical tank has radius 3 feet and height 10 feet. And it stands on a platform 50 feet high. Okay, so this is 50 feet. Okay. And the cylindrical tank is on the platform. Now, the question is, how much work will be done in filling the tank by pumping water from the ground level? So, the source of water is on the ground level. Okay, this is the platform and this is the circular tank. Now, it will be more convenient this time if we will let this be the x-axis and this be the y-axis. Okay. Now, if this is the element, of course, this is a circular element, no? With the thickness dy, okay, the thickness is the differential of y, and the radius is equal to 3 feet. Okay, all throughout the radius is 3 feet since this is a cylindrical tank. Okay, and of course, the differential dv is equal to pi r squared times the differential of y. And since r is equal to 3, then dv is equal to pi times 3 squared times the differential of y. Now, what about h, which is the distance of the element from the source of the water? Now, please take note that this distance is 50 and this is y, okay, from the x-axis. Hence, h is equal to 50, okay, 50 plus y. Therefore, the work done is equal to the density times the integral of h is 50 plus y. The differential of v is pi times 3 squared dy. And if we will simplify, then just bring out pi times 3 squared before the integral sign, and that will give us 9 pi times the density. Okay, and limit will go from, okay, since the height of the cylindrical tank is 10 feet, then it will go from 0 to 10, since the cylindrical tank will be filled with water by pumping it from the ground level. Okay, hence we will have integral from 0 to 10 of 50 plus y dy. Of course, the integral of 50 dy is 50y, and the integral of y dy is y squared over 2. And evaluating this from 0 to 10, okay, and multiplying it by 9 pi w, okay, when y is equal to the upper limit 10, that will give us 500 plus 50. Okay, sorry, 10 squares 100 over 250. And when y is equal to 0, everything is 0. So that will give us 9 pi w, okay, plus 50 times 10, so 550, okay, times 9 will give us 4,950 pi w foot-pounds. Now, this is the work done, okay, in filling this tank, cylindrical tank, okay, with water, where the water will come from uh, the ground, no, which is 50 feet from the platform. Okay, so this time it will be more convenient to make this as the x-axis and of course this as the y-axis. So we follow the same formula. The work done is equal to W times H times the differential of V. Okay, so this finishes the topic on uh, differential, definite integrals and its application.